Welcome to Math with Professor V. This is video lecture for section 3.1 on orthogonal trajectories for differential equations. Now, we say that two curves, let's call them L1 and L2, these curves are orthogonal at a point if and only if their tangent lines, T1 and T2, are perpendicular at the point of intersection. So what this means is that the slopes of the tangent lines are negative reciprocals of each other or opposite reciprocals of each other. Another way you'll see this definition is that the product of the slopes of these tangent lines is -1. Same thing. The only case where we have an exception is when the tangent lines are parallel to the coordinate axes. So anytime you would have a vertical and a horizontal line, then obviously the product of their slopes wouldn't be equal to -1 since vertical lines slopes are undefined. So I just wanted to give you an example right now of some curves visually so you can kind of imagine what's going on that are orthogonal. And here we have an ellipse and y equals x cubed. Here is y equals x cubed. Here is the ellipse, x squared plus 3y squared equals 4. And these two curves intersect at 1, 1 and -1, -1. Not only do they intersect at those points, the curves are orthogonal. So if you could imagine, say we draw a tangent line to the ellipse at that point of intersection, and then I also come along and I draw a tangent line to y equals x cubed, these tangent lines are perpendicular. And I can do the exact same thing right here. So that's what it means when we say two curves are orthogonal. The tangent lines at each of those points are perpendicular, okay? So how are we going to build on that now since we're in differential equations? Well, orthogonal trajectories are the first topic of study. Definition 3.1, orthogonal trajectories. So when all the curves of one family of curves, g of x, y, c1 equaling 0, intersect orthogonally all the curves of another family, h of x, y, c2 equaling 0, then the families are said to be orthogonal trajectories of each other. Meaning basically an orthogonal trajectory is any one curve that intersects every curve of another family at right angles. Now we say that we have families of curves here because we're allowing for this arbitrary constant here. But g of x, y, c1, this is one family of curves that varies based on what c1 is. And then h of x, y, c2 is another family of curves that varies based on what c2 is. And basically we say that they're orthogonal trajectories if all of the curves of this family intersect orthogonally with all of the curves of this family. Let's look at some examples because definitions can seem really overwhelming initially unless we put some sense to it. So if you have the graph of y equals -1/2 x plus 1, this is a line, and the slope of this line is -1/2, yes? It is an orthogonal trajectory of y equals 2x plus c1. I want you guys to notice something here. We can generalize and say that the families of y equals -1/2 x plus c2 and y equals 2x plus c1 are orthogonal trajectories. Because we know in order for these two lines to intersect at a right angle, in order for them to be perpendicular, all that's necessary is that these slopes are opposite reciprocals, which they are. It does not matter what the y-intercept is for each of the lines. So that's why it could be 1, it could be any arbitrary constant, which we can call C2. So we have a family of lines whose slope is -1/2 x that fits this criteria here. All of these lines are going to be perpendicular to this family of lines, right? Because it doesn't matter what the y-intercept is either here. We're just looking at the slopes. It's very cut and dry when you're dealing with linear functions, obviously. Let's look at something a little more involved. The graph of y equals 4x cubed, the one that we just saw earlier, is an orthogonal trajectory of x squared plus 3y squared equals c2. So this constant was arbitrary. The families y equals, and we didn't necessarily have to have a 4, it could be c1x cubed. and x squared plus 3y squared equals C2 are orthogonal trajectories. And you might say, that's a little hard for me to see, Professor V. How would we verify that? I'll show you. Okay, I'll show you. But looking back up here, basically the fact that this is a 1 is arbitrary. We could call that C1, and the fact that this is a 4 is also another arbitrary constant, okay? So they can vary by that much. And then lastly, here's another example. We have a family of hyperbolas, x squared minus y squared equals c. You could call it C1 if you want. And then we have the function y equals c over x. It could be C2. Notice these also are orthogonal trajectories, okay? So how do we go about and find it algebraically, right? So first you have to find the differential equation dy dx equals f of xy. Usually you're given first, not the differential equation, but you're given a family of curves. So you're given f of xy c1 or something like that. So you have to find the differential equation. Then you obtain the differential equation of the family of orthogonal curves to the given family. And you just take that by exactly opposite reciprocal. So once you have this here, dy dx equals f of xy, differential equation for the orthogonal family of curves would be -1 over f of xy. And then you solve this resulting differential equation using any appropriate method. So most of the time they're just either going to be separable or linear, okay? But any of the methods that you've previously learned for solving differential equations are fair game. Okay, so here we go. Example 1. Find the orthogonal trajectories of the given family of curves. So here we have y equals c1 times e to the negative x. So first I have to go ahead and find the differential equation for this family of curves. So I need to figure out what dy dx is. So differentiating with respect to x, c1 is just a constant. E to the negative x derivative is going to be negative e to the negative x. So the differential equation would be negative c1 e to the negative x. And then I'm noticing here c1 e to the negative x is just y. So then I can write dy dx equals -y. Good? That's crucial. Okay, from here, this tells me that the orthogonal trajectory would have the differential equation dy dx equals, and then you just take the opposite reciprocal here. So it would become positive 1 over y. Okay, now to figure out what the orthogonal trajectory is, I simply have to solve this differential equation now. So I'm looking, this guy's separable, so let me go ahead. I'll have y dy equals 1 times dx. Let's integrate both sides. Left-hand side is going to give us 1/2 y squared. And then antiderivative of 1 with respect to x is just x. Plus c. Remember, we only put the plus c on one side. And then notice here, I can't really find y as a function of x. So I'm just going to isolate y squared and multiply everything through by 2. So y squared equals 2x plus 2c. And then usually what we like to do is redefine this and say 2c is actually equal to c2. This is the arbitrary constant for my second family of curves, the orthogonal trajectory. And then we can write our final solution as y squared equals 2x plus c2. And that's usually how you'll see the answer written, like in the back of the book or somewhere like that. Because we use the arbitrary constant here, c1, for the first family of curves that was given. And then usually we'll switch it to c2 for our second family. Okay? All right, that was a warm-up, you guys. Let's be real. Let's do something spicier. Here we go. Okay. Here we have 2x squared plus y squared equals c1 squared. Can you tell what this would be? What this family of curves is? Ellipses, right? Very good. Okay. So first things first, we have to find the differential equation for this family of curves. So I'm going to differentiate with respect to x, and I'm going to do this implicitly, right? since I'm not given y explicitly as a function of x. So derivative of 2x squared is going to be 4x plus derivative of y squared with respect to x is 2y times dy dx. Good? If you forgot implicit differentiation, I have a video lecture for you, so you could just check the description of this video. It's there if you're rusty. And then c1 squared, c1's just a constant, so its derivative is going to be 0. Okay, now let's go ahead, let's solve for dy dx. So 2y dy dx equals negative 4x. And then dividing by 2y, I get dy dx equals negative 4x over 2y, which is negative 2x over y. Okay, so this is the differential equation for the given family of curves. This tells me the differential equation for the orthogonal trajectory is going to be the opposite reciprocal. Dy dx equals positive y over 2x. How are we doing? We're all right? Again, this one's separable, so let's go ahead and solve it that way. We have 1 over y dy equals 1 over 2x dx. Let's integrate both sides. Now be careful. So we have natural log absolute value of y on the left-hand side equals. Make your life easy. Remember, when you have this integral here, you can just think of taking the 1/2 outside, and then you have 1 over x dx. Then you don't have to use sub or do anything weird, okay? So antiderivative on the left-hand side is just going to be 1/2 natural log absolute value of x plus c. Okay, so let's see if we can clean up a little bit more, all right? What I'm going to do is multiply everybody through by 2. You'll see why in a hot second. So we have 2 natural log absolute value of y equals natural log absolute value of x plus 2c. Now from here we can use our properties of logarithms so we can simplify further. I'm going to move the coefficient here. Remember, we can make it the exponent on the argument. And why I'm excited to do this is because then if I have y squared, I know that's not going to be negative. I don't have to keep the absolute value bars right here. So I can rewrite the left-hand side as natural log y squared. And then another funky thing I'm going to do over here, which you're going to have to get used to doing to simplify. We have natural log absolute value of x plus natural log of e to the 2c. And basically, I'm just rewriting 2c as natural log e to the 2c. That way, again, I can use properties of logarithms and combine the two on the right-hand side. So then I have natural log absolute value of x times e to the 2c. Remember, you can do that. Okay, why am I excited? Because now, remember, logarithms are one-to-one functions. I can drop these and equate the arguments. So then I have y squared equals absolute value of x times e to the 2c. And then if you drop the absolute value bars, then you basically have plus or minus, right? Instead, x times e to the 2c. And now we're going to redefine our constant so that we can have a really cleaned up answer. So I'm going to say c2. Remember, we want to end with c2 as the constant for this orthogonal trajectory. c2 is going to be plus or minus e to the 2c. So then I can say now I have found the orthogonal trajectory. It's y squared equals c2x. Boom. Wasn't that slick? You might say, oh, Professor V, I would not have thought to do that. I know, sometimes you have to kind of just practice and build some experience for how the final answer should look and just check your work as you go. So I always tell my students, don't do the whole homework assignment and then check at the end whether or not you've been doing them correctly, because then if you were doing them wrong, right, you're just reinforcing those bad habits and not catching your mistake as soon as it happens. So you want to nip it in the bud if you make a little boo-boo. That way you can figure out what the right way is to do it immediately and you don't have any bad habits to break. Okay, now they're not all going to be separable. So I've got one more example for you. And this one I thought was a little spicy. Oh my goodness, we had to do something clever to solve it. So here, the family of curves is y equals negative x minus 1 plus c1 e to the x. Ooh, okay. So let's go ahead. Let's differentiate term by term, and we'll find the differential equation for this given family of curves. So derivative of y, dy dx, equals derivative of negative x, -1, derivative of -1 is 0, plus derivative of c1 e to the x is c1 e to the x. Now, you don't want to find the differential equation for the orthogonal trajectory when you have this C1 situation in here. Notice I want you to see a couple things that have happened so far. In the last problem, it was not an issue because when we took the derivative of C1 squared, it was 0. So then boom, we had differential equation for the given family, and then the differential equation for the orthogonal trajectory did not involve any of the arbitrary constants. In the very first example I did, remember, we were stuck with the constant, and the way I got rid of it was noticing that all of this I could replace with y. So we want to do something similar right now. Okay, we have to do something that we did like from this first example. Okay, so you go, oh no, I don't want this c1 e to the x. Well, look at the OG family of curves that was given to you. How can we get rid of c1 e to the x? We can solve for it. c1 e to the x is equal to y plus 1 plus x. I just moved these guys over. Did you see that? That was so slick. Okay, so then now we can say dy dx equals -1 plus y plus 1 plus x, which is just y plus x. Okay, whew. So let's look at the original differential equation now that we have dy dx equals y plus x. That means the orthogonal trajectories differential equation will be dy dx equals 1 over, or -1 over, excuse me, y plus x. Okay, so take a second, stare at this guy. How would you solve this? It's not separable, huh? Ew, ew, ew. It's not linear. What to do? We are semi-stuck. We are just semi-stuck. So what you do is you pull a little sneaky maneuver and you say, instead, let me consider the reciprocal. So dx dy would be, just flip both sides. Negative, keep the negative, y plus x, which is -y minus x. This actually is linear now. So dx dy plus x equals -y. I want you to think of the coefficient on x, which is just 1. Now that's basically our p of y. Remember, normally when we do linear equations, that's called p of x, but this is p of y instead, since our differential equation is dx dy. We're differentiating with respect to y. So we can go ahead, we can find the integrating factor. So our integrating factor is going to be a function of y this time, though. Ooh, so it's e raised to the integral of p of y dy, so 1 dy. So this is just e to the y. Then remember, we come through, multiply everybody in the differential equation by that integrating factor. So e to the y dx dy plus e to the y times x equals negative e to the y times y. Verify. This should always be the derivative, in this case with respect to y, of the integrating factor times x, not y in this case. Let's check. Is it true? I always check. I've caught myself making a boo-boo once in a while. Okay, if we differentiate with respect to y, we're going to do product rule. So leave e to the y alone. Derivative of x would be dx dy. We got that there. Plus derivative of e to the y is e to the y. Leave x alone. Perfect. Now to solve, let's integrate both sides with respect to y. The left-hand side's easy. You're just going to have e to the y times x. What about the right-hand side? Oh yeah, we have to do by parts. Okay, so let's pick u and dv. You could also do tabular if you want. u is negative y, pick the polynomial, and then dv is going to be e to the y dy. You could put the negative here, but I just don't like to. And then du would be negative 1 dy, and v is e to the y. How are we doing? Okay, so then by our by parts formula, the right-hand side is going to equal uv, so negative y e to the y minus integral of v du, which is going to become positive because we already have a negative here. So positive integral e to the y dy. Oh, we're home free. E to the y times x equals negative y e to the y plus antiderivative of e to the y is just e to the y. And then I'm going to put plus c. And then easiest thing is for us to just solve for x as a function of y. So I'm going to go ahead, divide everybody by e to the y. Okay, divide everyone by e to the y. So I have x equals negative y plus 1 plus c divided by e to the y. C divided by e to the y does not become another constant because this is a variable function. So all I can do is, let me just clean it up and write it as c e to the negative y. C e to the negative y. And then you might go, oh, but Professor V, aren't we supposed to end with C2 because we started with C1 for the given family? So yeah, we can, and we didn't have to redefine it at any point. So let's just call it C2 from the get-go. And then we are done. And then we are donezo. How did you like that one? You're like, I would have never thought to do that. Well, now I showed you. So hopefully next time you get stuck, maybe you'll think, oh, let me do a little flipperoo, switcheroo, okay? So just remember right here at this point, dy dx was negative 1 over y plus x. We were stuck. So just taking the reciprocal of both sides, then we have dx dy equals, the negative stays. All we were doing was taking the reciprocal of both sides. So then it just becomes negative y plus x, which then this is a linear differential equation, okay? I hope you enjoyed this video on orthogonal trajectories. Give it a thumbs up. Subscribe if you haven't already. If you want to watch the full video lectures playlist for differential equations, you do need to become a member of this channel. But this is a little bonus freebie. And if you need to review any of your other calculus topics, integration techniques, Calc 1, even if you're having a rough time, you forgot a little bit of algebra, log properties, it's all good. I got you. I have video lectures organized into playlists on pretty much every single topic in pre-calc, Calc 1, Calc 2, Calc 3. So just check it out. Also follow me on Instagram and TikTok until it gets banned. Who knows what's going on. Math with Professor V. I love you guys so much. I'll be back sooner than later. Bye.